subject of this and perhaps the next lecture is important, because we are going to discuss Gauss law, and this is the first law of electromagnetics. Okay, it was first Maxwell's equation, sorry, not law, first Maxwell's equation for electromagnetics. Now, Gauss law in free space can be formulated in terms of electric field. How? I know the electric field of a point charge. The electric field of a point charge is given by q by 4 pi epsilon 0 r square along the direction r. Okay. If I integrate this electric field over a surface, okay, of constant radius, if I integrate this one over a surface of a constant radius in the spherical coordinates, what do I get? We will try out what we get. So, what is dsr, which is the surface integral of a spherical coordinate system? I know what this is, right. This is r square sin theta d theta d phi at a given radius of a r at a given radius r of a unit sphere. This is the surface area element. Okay. So, this is the surface area element that we are looking for, and this is given by r square sin theta d theta d phi. Now, if I integrate this one, what do I get? I have q by 4 pi epsilon 0 r square multiplied by r square sin theta d theta going over d theta and d phi. So, theta goes from 0 to pi, whereas pi goes from 0 to 2 pi, correct. So, you will see that r square cancels with numerator and the denominator, q by 4 pi epsilon is actually a constant, and the remaining part with integral over d phi you are going to get a 2 pi, and an integral over sin theta from 0 to pi you are going to get another value of 2. So, you are essentially going to get 4 pi, which gets cancelled on both numerator and denominator. So, the result will be q by epsilon 0. Okay. If you do not think that this is interesting, consider if I bring these two together, what happens. Integral, not just any integral, this is a closed surface integral, right. So, this is a closed surface integral of the electric field, and I just used the surface of a spherical. You can actually imagine any other surface, right. It does not have to be spherical surface, it can be a cylindrical surface, it can be a point, it can be a cube, it could be any other surface, it could be a general kind of a surface. And in free space, this is true that if you take such a closed surface, and it is important, it has to be a closed surface, and then carry out the integral E dot ds on this, you are going to see that the value will be equal to total charge. Well, it is actually equal to charge by epsilon 0. So, I can actually push this epsilon 0 to the left hand side, and I get this expression, which is very interesting. It tells me that integral of electric field around a closed surface, on the closed surface, will be equal to the total charge enclosed, right. If I have a point charge here, I take a surface around this and then try to apply this equation. What I will find is, if the charge value is q, the integral answer, the left hand side will also give me q. What if my surface is like this, right, the one that I have shown in the dots? What will be the output here if you try to integrate the electric field? Well, the output will be equal to a big 0, because there is no charge enclosed here, no charge enclosed in this surface. So, as long as the surface is enclosing a charge, you are going to get charge, and such surfaces are called as Gaussian surfaces. A Gaussian surface is one which actually encloses, and it is a closed surface which is typically used to calculate the charge enclosed. Okay. Now, this is by itself may not have been very useful unless I do not know what is the electric field, but I can somehow guess what is the charge distribution. Okay. For most analytical problems which possess some sort of symmetry, this equation can be used, okay, to find electric field. We are going to do that couple of examples now, but this is the first Maxwell's equation in free space. This equation applies only in free space. Okay. What about situation when it is not free space? What if there is a medium in between? Well, for the medium in between, you have to define a new quantity called electric flux density. The importance of this electric flux density is this. I consider a parallel plate capacitor, for example, and then I apply a potential difference which causes an electric field between the two. This will be the electric field, it would all be located in between. Okay. This would be the electric field. Okay. There is a potential that I have applied to this parallel plate capacitor. What if I substitute the medium which was assumed to be air here from a medium which is different from air? What if I put wool or grass or a metal plate inside? What will happen to the field configuration? Well, what happens is that the field actually changes, because all this matter, wool, glass, metal, although these are different type of materials, they all are composed of atoms, and atoms are composed of nucleus and electrons. Okay. So that there are charges on the microscopic scale. So to any matter, if I apply an electric field, okay, through any matter, outside the matter the electric field will be E, outside it will be E, but what would be the electric field inside? It turns out that I have to consider this microscopic structure and find the electric field because of all the microscopic charges that are present inside. Now, as we have already seen earlier, there will be an enormous number of microscopic charges sitting inside, and to calculate or take into account every type of charge that is sitting inside and calculate the corresponding interactions will make the problem very tedious. So what we assume is that the material can be expressed in terms of some measurable quantities and will be defined by certain material properties. Okay. These are macroscopic material properties that we will assume that will describe the material. Much of this is not experimentally obtained, although there are very good experiments. Much of this is phenomenological, that is to say phenomenological means to say that you observe something, observe a phenomena and then postulate what could be the type of the material properties. Okay. If you just take a point charge, calculate the force here in free space, you are going to get some force in free space or vacuum. Okay. Now, if I fill this region in between by some material, the force will change from vacuum to say F with material in place. Now, I can use the ratio of vacuum to material, okay, and then call this ratio as epsilon r, okay, and this itself will tell me that there has been a material inserted, and for as far as the forces that I am measuring on the charges is concerned, that is all I need to know. I do not need to know what is happening in the internal details of this material in between. Okay. I do not need to know what is happening in the inside of the material. For all practical purposes, I just need to know what is this epsilon r, and I can use this as a characteristic of the material. Okay. However, please note that the electric fields are all generated by not by the charges inside, but rather by the free charges that you have. Okay. What we assume now is that these free charges do not give me the electric field, okay, in the sense that I am not going to determine the electric field from these charges. These free charges will actually give me the flux density D, which I am going to relate it to the electric field, right. If I replace this material from one material to another material, my epsilon r changes, right. So, I need actually a quantity that would be completely independent of the material that I am talking about, a quantity that I can use and then relate later to the electric field through the material properties. But as far as this one is concerned, I do not want to get stuck to a particular material, because if I get stuck to a particular material, then I have to find out all the interactions that are happening, and then I need to keep evaluating that interactions. Okay. So, because of that, we assume that free charges generate D, which is independent of the material properties, and the D will generate in turn electric field E, which the connection between the two is phenomenological and that describes the material properties. Okay. The electric field E is the one which gives you the force on the other charge. So, how does free charge generate D, or what is the relationship between the charges in general free charges rho v to the electric flux density D? This is given by Gauss's law, okay. And the relation between D and E is material dependent, and this is given mostly by phenomenological arguments or by some measurements plus phenomenological arguments. How does the electric field apply force on a charge is given by Lorentz force equation. Okay. So, this is the new structure. Earlier we have seen that free charges are there, free charges generate electric field will in turn exert a force on the charge. Now, because of the material properties, we have free charges generating D, D generating E, E generating force. In free space, you can define D as epsilon 0 into E or epsilon naught into E. So, that the equation which we had written, epsilon 0 integral surface integral of the electric field over the surface was equal to the total charge contained, can be replaced and written as the surface integral over this flux density D, that should be equal to the total charge contained. This is so important and this is called as Gauss's law. So, we are going to discuss applications of Gauss's law now. So, Gauss law tells you that if you take a closed surface and then integrate the electric flux density, you are going to get the total charge enclosed. Now, I know that charge enclosed can be in general written as the integral of the volume charge density. Okay. This equation is Gauss's law or Maxwell's first equation. I mean, first he did not actually number them, but it is something that we can conveniently take that, because this is the first equation that we are encountering, which will eventually become Maxwell's equation. Okay. So, this equation is Gauss's law or Maxwell's equation, Maxwell's first equation, and this is an example of an integral equation or an integral form of the law. Okay. Why integral form? Because there are integrations on both the left hand and the right hand side of this law. Okay. How useful is this Gauss's law for me? Consider the infinite line charge. We have seen the infinite line charge so many times, it might actually feel that we are actually revisiting just a friend. Okay. So, I do not have to explain too much about the line charge for you, except telling you that the line charge density is rho L coulomb per meter. See, we struggled a lot to find the electric field because of this infinite line charge, right. We first started with Cartesian coordinate system, we had to do 3 integrations and we found out that that problem could be simplified somewhat by using a different coordinate system which was much better suited for it, which was cylindrical coordinate system. Then again we could use symmetry to deduce that the only electric field component that we are going to get will be radial component, and that the electric field will also be radially directed. Okay. So, we saw that in the last class. Now, we will still use the symmetry arguments, but let us apply Gauss's law to find out what will be the expression for electric field. Okay. To find Gauss's law, I need to first find the Gaussian surface. Let me assume a Gaussian surface which is cylindrical in nature. Okay. This is a Gaussian surface that I am applying. This is a cylindrical Gaussian surface, okay, of some height h. Does not matter what is the height of this one, this is some height h, okay, and this is at a radius of r. Okay. This is a radius of r. This r could be anything, you are just imagining different cylinders of different radius r. So, you fix a radius of the cylinder in this case to equal to r, and of course, r itself can be variable, and the height of the cylinder is h. Now, how many faces does this cylinder have? 3 faces, top, bottom and the curved surface, right. Now, symmetry already tells us that no matter where on this surface point on the cylindrical surface I am located, symmetry already tells me that there cannot be a z component, there cannot be a phi component, correct. So, the only components that I can have will be along the radial component, and that is good for us, because on the curved surface the surface of a cylinder is given by r d phi dz, right, going along the radial direction. So, I can substitute that into this expression. So, I have the closed surface integral broken up into 3 parts, top, bottom and curved. So, I can consider the curved surface integral, which will be d dot r d phi dz and r dot. So, clearly if d has components of r, phi and z, correct, the only component that will be non-zero in this expression will be the dr component. So, writing that as dr, so writing d as dr r hat plus d phi phi hat plus dz z hat. Okay. I can see that the dot product of r will make r dot phi go away, r dot z go away. So, I the inside of this one for the curved surface will be just dr r d phi dz. What are the values of d phi and dz? Well, for this curved surface phi should go from 0 to 2 pi and z would go from any point which will in total give me a height of h. Okay. So, let us say this is some a to b such that b minus a is equal to h, then this integral will be a to b. Okay. This is the expression, right, to the left side of the Gauss's law. This is left side of the Gauss's law. Now, I can proceed to do the integral over here if I know that dr will not be a function of phi and z, and we know that dr is not going to be a function of phi and z. Because of symmetry, if you move around the line charge, you are going to see the same line charge everywhere. So, dr cannot be a function of phi. Similarly, you move up and down the cylinder on the infinite line charge, you are going to see the same line charge, which means that dr will again be independent of z. So, dr is a function of r only, okay, and this is the integral over phi and z. However, this is crucial, dr of r is actually a constant. Well, I just said that dr is a function of r, but how could it be constant? Well, remember this is constant at constant r, right. So, I am actually considering a cylinder at constant r, therefore, on that constant value dr will be a constant. So, which means that I can move this dr out of the integral, so that I am left with r d phi dz. R will also be a constant, so r can also be moved out, okay, and I am left with integral from 0 to 2 pi integral a to b. So, if you evaluate this one, you are going to get dr 2 pi r into h. This is the left side of Gauss's law. What about the right side? To get the right side, you need to know what is the total charge that is enclosed here by the surface. The charge is enclosed only on the line. So, what is the total charge enclosed? Total charge enclosed will be the integral of the line charge, right. So, you have rho l and then dz over the same height a to b, and this will be equal to rho l into h. Now, equate the left hand side and the right hand side of the Gauss's law, so that you obtain dr as rho l by 2 pi r. Dr will be also equal to epsilon 0 into Er, right, in free space. Assuming that this is in free space, this will be equal to epsilon 0 Er, which implies that electric field will be radial, and it is given by rho l by 2 pi epsilon 0 r volt per meter along the radial direction. Okay. Now, let me get you to a different charge distribution. We have seen line charges enough that it might bore us. So, we will look at infinite sheet charge. Okay. There is a hard way of doing this problem and there is an easier way of doing this problem. What we mean here is that there is a infinite sheet of charge that we have placed. Okay. So, this is x, this is y. So, I have placed this charge at x is equal, sorry, z is equal to 0 plane, and I want to find out the electric field at any point here. How do I find the electric field? Well, choose again Gaussian surface. Okay. So, although I have drawn lines here, this should actually be a surface. Okay. This should be a surface for me. Let us proceed by writing the block. Okay. So, I take cube, okay, and then cover the cube such that the cube is halfway between. So, this is the surface, the cube, the top surface of the cube is located at some height along z, and the bottom surface is located at z is equal to minus h. Okay. What will be the electric field? Consider a point here. Okay. Consider a point on the surface. Now, for every point that is sitting here, I can actually find from the surface charge, I can find 2 points such that, or 2 lines such that their electric fields will be directed in this way, but their resultant of the 2 electric fields will be directed along z axis. Okay. So, you can imagine that this is a plane charge that I am showing. Okay. This is a plane charge that we have. For this plane charge, I am going to consider a Gaussian surface. That Gaussian surface will be halfway located like this. Okay. For this halfway located surface, this is z is equal to h, this is z is equal to minus h. Now, on this point, right, now imagine that on this point I am going to find the electric field. There is a line here, or there is a line inside this surface which would run like this, there is another line that would run like this, there is a along this line the line charges are all uniform, right. I can actually think of a plane of charge as an infinite number of line charges, right. A plane of charge can be written as infinite number of line charges. So, this line charge which is running here, and you have to imagine the box here, would give me an electric field in this direction, right, because at this point I want to find the electric field, it would give me an electric field in this direction. Similarly, there will be an electric field because of another line charge at the same distance and the same magnitude. So, this would also be directed in this way. Now, I have two charges, one directed this way, two forces, one directed this way, the other one directed this way. So, the resultant electric field or resultant D field would have to be perpendicular, and it would be along the z direction. Okay. You can do this for any point on the box that we have considered. So, at any point on the pill box that we have considered, you can show that there are two line charges which give you electric fields of equal magnitude, such that the resultant electric field is always along z axis. Okay. Then I know that the D field is going to be along z axis only, right. So, it will be say z dz. Okay. So, what will happen to the left hand side of the Gauss's law? It would be integral of dz over the surface area. Now, what is the surface area here? The surface area is directed along z axis, and I know what is the surface area, that is nothing but dx dy over a surface delta x delta y, right. That is to say, the surface that I am considering will have delta y and delta x, so that the area of this surface total will be equal to dz delta x delta y. Okay. This is the left hand side of the Gauss's law. Why was this happening? Because at any point on the surface I could consider there were two equal line charges which would give me the electric field which was away from z, and it would actually be constant. Okay. Similarly, there will be electric field at the or the D field at the bottom, they would also be obtained because of two equal magnitude lines, and the resultant will be along minus z direction. So, therefore, the total D field that is here will be 2 times this value. Okay. Why 2 times? Because the total flux enclosed or the total flux that is coming out after integrating will be on this top plate dz is along z, but on this bottom plate the surface area is along minus z, right. The surface area is along minus z, and the D field is along also minus z. Okay. So, they will essentially add up, nothing will happen to the side, because the electric field is not, or the D field is not present there at all. D field is all directed along z, and the surface area onto the right and the left as well as back and the front will not contribute anything to this integral. So, I have the left hand side as 2 dz delta x delta y, the right hand side will be the total charge enclosed. What would be the total charge? If I assume a uniform uniform surface charge density of rho s coulomb per meter square, which is entirely on the z equal to 0 plane, the total charge enclosed by this surface area will be rho s into delta x delta y, which will give me dz of rho s by 2. Electric field Ez will be equal to rho s by 2 epsilon 0, right. So, this is interesting because the electric field is directed entirely along the z axis, and that this electric field is completely constant. It is not depending on x, not depending on y, not depending on z. The electric field is the same strength as it is at 100 meters as it would be at 1 million kilometers from the source, right. Of course, this is completely an idealization, but a good example would be this tube light. Okay. So, if I had only one tube light here, the lighting that the tube light provides would essentially have the same strength near the tube light or on this table or on the floor. Okay. So, it does not change anything. If I go from here, I am seeing the exact illumination, and if I take it to the top, I am seeing the exact illumination.